So we have a tap, and there's water going out of the tap straight down to the ground. And now we know at point 1, which is right outside of the tap, the cross-sectional area A1 of the water stream would be 1.2 square centimeter. And at point 2, which is right above the ground, the cross-sectional area A2 would be 0.3 square centimeter. And we want to find the flow rate at 1 and the Reynolds number at 2. In this question, we'll be using both the Bernoulli equation and the continuity equation. So one form of the Bernoulli equation can be written as P1 minus P2 divided by gamma plus Z1 minus Z2 plus V1 squared minus V2 squared over 2G equals 0. And since we know the pressure at right outside of the tap and the pressure right above the ground are both atmospheric pressure, so P1 equals P2, so P1 minus P2 is 0, and we can cancel out this term. And we know Z1 minus Z2 will just be the height h, which is 50 centimeters. So we can simplify this equation to V2 squared minus V1 squared equals 2GH. And for the continuity equation, we have Q equals V1A1 equals V2A2. And we can see that the flow rate at point 2 equals the flow rate at point 1. So we can use either V1 or V2 for the calculation of flow rate. And we know that V1 equals, so we rearrange this equation. We have V1 equals A2 over A1 times V2. And we know that A2 is 0.3 and A1 is 1.2. So V1 will be 1 over 4 V2. So we substitute this equation back into our simplified Bernoulli's equation. We will have V2 squared minus V2 squared over 4 squared, which is 16, equals 2 times, so since we're using centimeters as our unit, G will be 981 centimeters per second squared times H, which is 50 centimeters. And we can use a calculator to solve for V2, which is 323 centimeters per second. So the flow rate Q equals V2A2, so 323 times 0.3 will give us 97 cubic centimeters per second. And now let's find our Reynolds number. So RE, the formula for Reynolds number is RE equals VD over the kinematic viscosity of, here will be the kinematic viscosity of water. And D will be the diameter of a pipeline or a streamline. So RE at point 2 will be V2D2 over dynamic viscosity. And here we have D2 will be, let's assume let's assume our stream is a cylindrical shape. So since we know cross-sectional area A2, we will have D2 equals square root of 4 over pi A2 equals 0.62 centimeters. And R2, so RE2 would just be so 97, oh no, V2. So V2 is 323 times 0.62 divided by, here's the viscosity. Since we are using centimeter as our unit, we need to convert the viscosity written. So this is the viscosity written in terms of meters, and now we need to convert it to centimeters. So since so the viscosity symbol, I don't remember what it's called in Greek letter, but that was proportional to meter squared, and now we wanted to convert it to centimeters squared, so that will be 10 to the negative 6 times 10 squared squared, so that will give us 10 to the negative 2 power. So plug this in the calculator and we will have our Reynolds number as 2.0 times 10 to the 4th, and that will pretty much be turbulent, no debate.